All right, let's start. Welcome everybody for today's third webinar this week around Spine project and our showing you what we've done in the project. So to start, I'd like to just say how wonderful this Spine project has been. I've been in EU projects before, but I think in here we've done something quite special, since we've all been really working together to build the things we've built. Even though in projects, in EU projects especially, you typically have certain responsibilities for certain partners and they take care of those, and that's it. I would just stress how different this has been as an experience, because it really didn't matter whose responsibility something was. People did what they knew how to best do, and together we have made something that we can really be proud of. So today we will see something out of that collaboration that shows more what the Spine can do, especially the SpineOpt model, what it can do when you go into more detail to the capabilities that's built into the Spine model, or SpineOpt as we call it, and then we use the case studies we have. Those case studies are not intended to be deep case studies that would really make a contribution to a specific research topic. They're more about making sure that we have the capabilities to model different things in the SpineOpt environment, and I think they're very good for that, and many of them are available in the Spine GitHub pages as repositories that you can try out yourselves. So I will let the people introduce themselves when they will speak. I think I didn't say anything about myself. I'm Juha Kiviluoma and being the project coordinator. And the project, of course, has been funded by EU, and we should have this as a note here. And then we have these other webinars. So two have been already were yesterday and the day before. They will be available in our through our webpage in early next week, and then we will have one more webinar tomorrow about the Spine interface, which shows you how you can use Julia Jump and Spine Toolbox directly together to build new models in a rather rapid way. But today we will go to the case studies, and please note that the webinar is recorded and again made available. And you've all been turned off, and you can't unmute yourselves unless we do that. But you can ask questions. So you can ask them in the chat during the presentation, and depending whether it's a technical question we can answer right away, we will do that in the chat. Or if it's a more open discussive question, then we can take it up at the Q&A. You can also save your questions for the Q&A and raise your hand during the Q&A, so we can unmute you and you can ask the question. Or you can also use the chat during the Q&A. So with that, I will turn the presentation to Manuel Marin.
Thank you, Juha. Hi, everybody. Thanks for coming today. My name is Manuel Marin. I'm with KD8 in Sweden. And I will be taking these two first sections here. So a brief introduction to Spine, what is it? And then the first of our case studies that we want to present you today about hydropower. So what is Spine? Basically, one way to speak of Spine is by speaking of its main two components, which are seen in this slide here. So on the left, in this red box, we have what we call Spine Toolbox, which is basically a GUI that you can use to build a workflow. And the workflow represents some operation you want to do in data, over some data. And you want to do it step by step. So for example, typically when it comes to energy systems modeling, you have your data in an input file, and then you want to pass that data to a tool that runs some optimization and then writes that data into an output file. And you can design those kind of workflows in a Spine Toolbox. It doesn't need to be energy systems related at all. So it's a very generic tool. It can be whatever you want, as long as it's data processing, basically. But we have a SpineOpt, which is energy systems related, and we use the multi-energy systems concept to refer to systems that combine multiple vectors or sectors, whatever you want to call them. And this is something, this is a model generator that you can use with Spine Toolbox. So SpineOpt can be the tool that you use with Spine Toolbox to run or to model an energy systems, basically. And it has a specific data structure that I will talk about next. So this is the basic setup. A little bit more detail in a Spine Toolbox. We have this is kind of the workflow that you would be building typically. So basically you have like, so this is our favorite one. You have this is the one that we will be using, I think, most of the times for this presentation today. It's basically a data store item that holds data in a Spine format. So the Spine format is something we have built to represent systems in a very flexible way. So you have your data here, and you have this arrow that goes into this hammer here, which is a tool. And it's basically something that does a computation on data. In practical terms, it's like a script, a programming script that you write, and you call your model from that script. And then it writes results to another data store, which is at the output of this tool. So there's an arrow going in this direction as well. So this is kind of the basic workflow that we have. But you can have a little bit more than that. At the input side, you can have data that is not in the Spine format. That's often the case, that you don't want to enter your data directly in this database here. You want to have it in like an Excel file or a CSV file, because that's often the case, and it doesn't depend on you. And for that, we have these two items here that help bringing that data into the Spine format, so it can be used by the tools that understand the Spine data. So this blue file here represents this data connection to a file or to a database or whatever. And this importer allows you to specify how this data has to be understood in order to be imported into the Spine data store. And the nice thing about this is that you can set up all this, and then it's repeatable. You can execute it as many times as you want. And if you happen to have more data available at the source at some point, you can run your workflow again, and the data will come into the Spine data store magically. Something similar can be done at the output. So if you have data in a Spine data store that's the result of your model, and you don't want to have it in the Spine format, you can export it to another format if you want, like CSV and stuff like that. So SpineOpt comes here. It's one of the tools that you might want to run. And SpineOpt is basically a model generator that understands data in the Spine format, provided that the data has some specific names that are the names that SpineOpt understands, and they are hard-coded in the code, basically. And these names are right here, so you can have like the model class that you can use to describe a little bit some general things about your model. And you have the temporal block class that you can use to specify a temporal structure. And And something similar here, stochastic structure, you can link that with stochastic scenarios to build a stochastic structure for your model. And then you have your system objects that represent your actual energy system. And these are almost self-explanatory, so you can have nodes that represent energy balances and connections that transfer energy across nodes and units that convert energy between nodes. And optionally, you can also explicitly state what's the commodity that belongs to each node. And all these classes and objects are related, and you are responsible as a user to build these relationships in order to specify your energy system. Sorry. So I have a motivating example here. Let's say that we have these very simple multi-energy systems where we have where we have like a fuel supply that is infinite, 2 power plants with different specifications here that take fuel from this node and produce electricity to satisfy a demand that it's modeled at an electricity node. So pretty simple, and I will show you how this looks in Spine Toolbox right away. So I hope you can all see my screen. So this is the, oh sorry, I have a bunch of messages coming here. So this is the Spine Toolbox GUI. This is the main GUI you have. And this space here is where you build your workflow. So you might recognize this from a couple of slides ago. Here I have an input data store, a tool that runs SpineOpt, and then an output data store to collect results. And you can inspect each of these elements. So if I double click this input here, I can see the database basically. And on this part, you might recognize the object classes I was talking to you about. And if you expand this, you can see what are the objects that are created for these classes. So you see that here we have electricity node, fuel node already. I built all this offline, if you're wondering. I entered all this data. Here I have my power plants. And I wanted to show you that I can have a graphical representation of the system here. So I can basically see what's going on. And you can see here that here I have like the model objects. So I have a model objects, basic objects that I need. And I have defined a stochastic structure with one scenario and a flat temporal structure. And I have some report data here to write the results I want. And in here I have my system. So you see I have the fuel node, I have the power plants, and I have the electricity node. And when I select this, I can see some parameter values here. So for example, for the fuel node, I have a parameter called balance type, which is again a name that SpineOpt understands. And I'm specifying this value to tell SpineOpt that this is an infinite supply that doesn't need any load balance or any balance, energy balance. For the electricity node, I have defined a demand of 200. And for the power plants, I have defined like the cost, which has this name that again is intended to be consumed by SpineOpt. And I have the fixed ratio at which this unit converts energy from fuel to electricity. And I have a capacity, and I have the same, something similar for the power plant B. And this is my input database. The script that runs SpineOpt on this database is pretty simple. We just import a Julia package where we have developed all the code that we need to build an optimization problem from the data and solve it. And this is the instruction that's doing exactly that. And I won't run it, but I will show you the results from a previous run, which are here. And I have this pivot view here that I can use to see results. So you can see, for example, that I have a single scenario here, which is my realization, and I have the unit flow, which is a variable from a SpineOpt, and here I'm seeing the result. And I'm seeing what each power plant is producing into the electricity node, so 100 megawatt hours each. and this is what they are consuming from the fuel node. And I can, of course, I guess I can pivot this in any way. So that's it. That's how it works. I hope you got the main idea. Let me stop sharing, and if you, Toby, can restart, please, the presentation. Thanks. Are you gonna go to the next slide, or should I just take control?
Just take control, Manuel.
Okay. Oh yeah, this is easy. So now, next thing in line is this hydro case study. So this was one of our first case studies, and this is actually like a proper energy system that we want to model. That's not trivial, and we have this objective here, which is to model 1 week of the operation of one of the rivers in the Swedish hydropower system. And we have chosen the Skellefteå River, which is in northern Sweden. You can see this. This is clearly an evidence that this is up north. And this is one of the power stations, and we want to model this, basically. And this model, I should say right away, it combines water flows with electricity flows. And we have some input data for each of the 15 power stations in this river. We know like the parameters, including the capacity of the turbine, at which ratio it converts water to electricity. We also have this reservoir level parameters, so initial, final, and maximum level. We have some constraint on the minimum water discharge and spillage per hour that each power plant needs to respect. And of course, we know the topology of the river, so we know what's a downstream station for each one of the stations. We know which one is next in line. And how long does it take for the water to reach that station? And this time can depend on whether the water is spilled or discharged through the turbine. We also have the local inflow per hour, so the water that's coming to the reservoir from melting snow or whatever, and some average water discharge per hour that it kind of gives information on what's the steady state of the river. And then we have the electricity prices during the week that we will use like to maximize our income. And so we assume that the system is operated rationally, basically. So we want to maximize profit from electricity over the week. And we need to assume, because we have delays on the river, we need to know what was happening before the start of the simulation. So we need to assume something about that, and we are assuming that all power plants have been discharging the average amount of water before the beginning of the week. So with that, we can start building our SpineOpt data structure to model this. And here I have a schematic that basically explains everything, hopefully. This is one power station, and you can imagine that the same is replicated 15 times for all the power stations. And what we have here is, well, these nodes. So this is Rebnis power, the Rebnis power station. And the downstream station is Bergnäs. So this node represents the entrance to the station. So it's like the upper part of the reservoir. And this is the upper part of the downstream reservoir, the next one. So water can follow two paths from this node into the next station. Water can be spilled, that's one of the options, and it goes through this connection into the next node. Or water can also be discharged, and it goes through the power plant into a lower node and then to the next station. So obviously, when it goes through the power plant, it produces electricity, and that electricity is sent to an electricity node, and from the electricity node, it's withdrawn by an electricity load that has a cost that corresponds to the negative electricity price. And that's how we make money, basically. So once we have this structure, all we need to do to use SpineOpt basically is to specify some parameters to describe how this is supposed to operate. And these are all the parameters that we need to specify for this system. And for example, for the Revnis upper node, we need to specify that it has a state, and that means that this node is able to store water because it's a reservoir. And it has a fixed node state because the initial and final level are fixed, so we can specify that using this fixed node state parameter. And it also has a demand that we use to express the inflow, so it's a negative demand because water is entering the node, basically. And then you see that on the link from the Revnis upper node to the power plant, we have the capacity. And then in the Revnis power plant, we have the fixed ratio out in unit flow that corresponds to the conversion ratio of this unit. And then in the electricity load, as I was saying, we have the VOM cost, which corresponds to the negative electricity price. And finally, in the connections, we have the connection delay that tells SpineOpt how long it takes for the water to reach the next station. So SpineOpt can introduce the proper delays in the equations. And that's it. This runs. I have two plots here that prove that. So this is the total electricity production over the week for all the power plants combined. And here I just picked some random curves. So this is the reservoir level for the 3 largest stations. We see that it follows a trajectory that it's supposed to be optimal if the solver is working properly. And I also, well, we have published this in paper. And I also wanted to show you briefly the Spine Toolbox workflow that makes this possible. So I will share my screen again. Let me start the Spine Toolbox again. So this was the previous project I was showing you. Spine Toolbox works with projects, so I have a bunch of projects here that I have created, and I have this case study A5 project, which is the one I'm talking about now. So you see that it's the exact same workflow: input data store, tool that runs SpineOpt and writes results to an output data store. So I wanted to show you some data here. I just wanted you to look at the topology of the river that we can beautifully see, in my opinion, using this graph diagram. So here is the entire system. If you go from outside to inside, so going into this center here, outside you have the water system, so the river, and in the middle you have the electricity node and the electricity load, and you see that all power plants are releasing electricity into this node, and then they are making that electricity by taking water from the reservoirs. So that's how it works, and I can also get rid of this one, so I can just prune that electricity node, and basically I have gotten rid of the electricity system, and here I only see the water system, and I can clearly see the river with the reservoirs, the power plants that produces the electricity, and then the connections that link each station to the next. So this river doesn't have much branching. It's just like a line, except at the beginning where we have 2 stations that release onto the same Bergnas station. So this is how it look. We can also look at the output data, but there's not much to say here. I showed you most of it in my presentation, but for example, I can show you again that for the electricity load, I have this time series that corresponds actually to the total electricity production over the week. You see that I have the same time series multiple times, and this is because I have run the model multiple times for some reason. And each run is written into a separate alternative, so I can compare different runs. If I have changed the input data, for example, I could look at different results. It's not the case here, but you get the idea. So that's it. I can stop sharing now and give the floor to our next presenter, which I think it's Topi.
Yep, I believe you are right. Just a second. Looks like the sharing the PowerPoint presentation is taking a while for whatever reason. Hello, can you actually hear me?
Yes, and you can turn your camera on if you want.
I tried. It seems my Teams is experiencing some technical difficulties at the moment. I'm just going to quickly leave and rejoin.
Yeah, we've noticed that it's not easy to build software when we've been doing this, and we also sometimes see that it's not easy for Microsoft either. We had some trouble when we were testing this system, but
yeah, apparently I can't even leave the meeting, so I'll just quickly terminate my entire Teams and try again.
Right. If you have any questions in the meanwhile, happy to take that.
Okay, attempt number 2. Can you see/hear me?
Hear you, yes, not see.
No? I should have my camera on.
Now coming. And we can see the slide, but we can't see you. That's okay.
Okay. At least the slides seem to be working, so that's progress. But you can't see me, is that correct?
Yeah, we can manage.
I can quickly try to turn the camera off and on again, but if that doesn't work, I'm just going to
It works.
Yeah, but now I can't see the slides. So yeah. Good job, Teams. Okay.
I can see the slides.
Now it's all good.
Except I don't have control over the slides. I don't think.
Manuel, there is a question now in the chat. Maybe you answer that while Topi figures out. I can also, Topi, take control and go to the slides.
Yeah, please do. I can't actually, like my Teams is just, I'm not seeing anything at the moment. Which is getting a bit.
I will answer that question in the chat. Thanks for the question. It's a nice one.
Okay. Thanks, Juha. Now I should be able to take control, I believe. Okay. Great. So I hope you're seeing the screen. If someone can quickly confirm. Juha or Maren or someone.
Yes.
Okay, excellent. So yeah, sorry about the technical difficulties. My name is Topi Rasku. I'm from VTT, and I'll be briefly talking about our case study called Case Study A4, which had to do with modeling building stock heating demand. So a very brief motivation as to why we wanted to do this. Well, a heating and cooling of the built environment is actually quite a big consumer of final energy in the European Union. And decarbonizing the heating and cooling sector isn't necessarily straightforward. electrification is one possible alternative. And via electrification, there's quite a large potential for possible flexible demand for demand response or demand side management purposes that might be worth looking into. So the objective of this case study was to demonstrate that you can actually model flexible heating and cooling demand in SpineOpt alongside these sort of more traditional economic dispatch and unit commitment models for power and district heating system. So on this slide, I have an illustration of the model that I used. I don't have the SpineOpt databases on my computer anymore. This case study was done over a year ago, and I think this illustration is easier to follow. But basically, on the left here, I have the illustration of the sort of very simple model that we had for the Finnish the Finnish power and district heating system. So basically, Finland was just divided into two nodes, one for the southern Finland and one for northern Finland. And for each of these nodes, we had time series for electricity demand, district heating demand, as well as sort of very simple aggregated capacity, like generation technology type modeling of the power plants. So we didn't model individual power plants, but we had like different power plants for different fuels, combined power and heat production, heat-only boilers, as well as electric boilers represented in this simple power and district heating system that we had here. In addition to that, we had a rather simple depiction of the flexible heating demand in electrically heated detached houses in Finland. And how this model worked is that we basically first calculated the properties of an average electrically heated detached house, both in southern and northern Finland. And then we created this sort of simple so-called lumped capacitance thermal model of that average building. And basically how these lumped capacitance thermal models work is that you have the building represented by a very limited number of temperature nodes. In this case, we had a temperature for the interior air temperature, which is the most important one because that is most closely related to thermal comfort, which is a boundary condition for your model or a constraint on your model. The rest of the building was divided into structural mass node, which included all the other structures besides the floor, which was modeled as its separate temperature node. Now, the heat demand for these types of models comes from these heat diffusion between these temperature nodes. So depending on the temperatures of these nodes, they exchange heat between each other, as well as the ambient conditions. So these temperature nodes depicting the building were constantly interacting with ambient conditions like ambient air temperatures, solar and internal heat gains, as well as ambient ground temperatures. So basically what's on the rightmost edge of the figure is what depicts the building heat demand dynamics. And what we have in the middle here is the simple depiction of the heating systems in these buildings. And these also included temperature nodes for the domestic hot water tank, as well as the hydronic heat distribution system. But where the linking between this building model and the power system model happens is via these units here, which represent the electric heating systems. So basically, we simply had a electric resistance heater for the domestic hot water system, which takes electricity from the electricity system and converts it into heat in the domestic hot water tank. And similarly for the space heating system, you simply take the electricity here, have it go the unit through the space heating system and be converted into heat on the heating system node. And this whole system was optimized using SpineOpt for a year-long rolling horizon optimization problem with an hourly time resolution. Now, what we wanted to do in this case study was to compare the results of this model in SpineOpt, which is the modeling tool we've developed in the Spine project, against our, I should say, against VTT's old backbone model, which we have been using for studies like this in the past. So we wanted to sort of compare the performance of these models and the results of these models. And this is basically an illustration of the Spine Toolbox workflow. And I'm going to quickly walk you through it. So the first thing that happens is we had this power system input data, which is the input data for only the power and district heating system models that we have, which then goes through an importer and into the data store, as Manuel previously explained. And then we had both SpineOpt and Backbone run the optimization for only the power system. So this doesn't include the building model yet at all, and produce results for the standalone power system. And these results were then compared between SpineOpt and Backbone. And the second part was the input for the building model only, which again go through an importer and into an input database. And again, it goes through this run building model tool, which again is just running either SpineOpt or Backbone to produce the building model results. And in this case, when we were running the building model standalone, the only sort of optimization the building model is doing by its own is it's minimizing the electricity consumption needed to keep the buildings at comfortable temperatures. So it's basically just minimizing the amount of energy needed to keep the buildings heated. And this result was used as a sort of baseline for the combined model in this case. And what the combined model does, well, first it takes the power system input data and the building model input data and combines them into a single set input data set, which contains both models at once. And then it also takes the electricity consumption, the baseline electricity consumption calculated by the building only model, and subtracts that electricity consumption from the electricity consumption data in the power system side only. Because in this case study, we didn't want to add any additional electrical heating demand on the system. We simply wanted to sort of take existing electrical heating already in the system and model it as if it was flexible. So we first had to calculate the baseline, shave it off, and then optimize the model again, but this time with the electrical heating demand being represented as a flexible resource. And again, this combined input data goes to the combined model part here, which again is just running SpineOpt or Backbone with different input data, this time containing all this, and producing results. And again, these results we compared between SpineOpt and Backbone. Now, in principle, I could have done this case study in one single massive Spine Toolbox project, where I would have basically this workflow duplicated for both SpineOpt and Backbone, and then also automatize comparing the results between the input databases. However, I didn't do that, and I thought it was easier to just show this part here anyway to avoid completely overwhelming you. But yeah, I hope that gave you some idea about what the process of making a case study in this case looks like. So now I'm just going to quickly show you some results. So these are some results from the comparison between the building only model. So on the top, on the bottom left here, I have the electricity consumption of the modeled space heating equipment in northern Finland in megawatts. And you probably can't see the difference. There is a blue line, which are the Backbone results, and then there is the red line, which are SpineOpt results. It's abbreviated SM here because back when I did this case study, it was still called Spine model. But the point is that the building only model behavior is basically identical. On the bottom here, I have also included the normalized mean absolute error between these two models, and it's pretty insignificant. And similarly on the right, I have a figure about the cumulative objective function value comparison between the SpineOpt and Backbone, which again, you can't really even see the difference. However, for the combined model, which included both the district heating and power system and the building models, we started to see a bit of a difference. And the main reason for this is that is shown in the bottom left. So here I have a figure of the total aggregated stored hydropower in southern Finland in megawatt hours. And you can see that in the spring, both models use the hydropower almost identically. However, during early summer, the two models start to diverge. And because this was a rolling horizon optimization, and you have very long-term energy storages in form of hydropower reservoirs, these sort of little differences tend to compound. And the model behavior starts diverging during a rolling horizon. But ultimately, both models ended up in rather similar situation by the end of the year. You can also see that the cumulative objective functions differ slightly. Backbone had a slightly better or lower costs over the whole year than SpineOpt, sorry. But overall, the differences were rather minor, and both models were performing reasonably. So, yeah. But yeah, some very brief conclusions or takeaways, however you want to call them. But in any case, the case study succeeded in what it was doing. It demonstrated that, okay, SpineOpt can model or handle simple lumped capacitance thermal models of buildings. And because of that, you can co-optimize flexible heating and cooling demand along with power and district heating systems. So yeah, hope you found this interesting. And I believe next in the agenda, we have a scheduled break time and a Manuel, Maren, someone, please correct me if I'm wrong, but I believe we have a 5-minute break scheduled.
I think we have 15 minutes break.
15 minutes?
Yeah.
Yes, that's also what I found. 15 minutes it should be.
Cool. Well, that's going to be easy because then we'll just see at for me, it's 4 o'clock. For you, it's 5 o'clock, I believe.
We're being very generous here, but it is in the agenda, so let's do that.
Okay. But yeah, so feel free to take a break. See you back at the, there's a saying
top
for
of
this
the hour.
Top of the hour. Thank you. But yeah, if you have any questions, ask them in chat. We'll probably be answering them during the break as well, but see you in 15 minutes.
Hello, welcome back, everyone. Welcome. I'm Maren Ideman, the next speaker. I hope you all made it back safe and sound from the coffee break or tea break. And yes, thanks, Manuel. Thanks, Topi, for your presentations already. And it's my pleasure to take you through our gas grid case study for the next 10 minutes. And before we jump into the setup of this particular case study, I would quickly like to take a step back, look at the motivation and the objective of this case study. So why do we bother? Why would it be maybe important to look a bit more in detail on how a gas grid works? Well, you all know that there is an increasing share of variable renewable energy sources that bring some uncertainties with themselves. And we know that gas plants can be a useful tool to provide flexibility options to ensure system reliability. So we want to be able to study those cross-sectoral interactions and analyze the potential of line packs. And line packs I refer to as a storage ability of pipelines. So this brings us to the goal, or the aim of this case study is to be able with SpineOpt to co-optimize the operation of the power and gas dispatch. And we want to include some technical detail here. So we want to have DC power flow on the one side, and we want to also allow for pressure-driven gas transfer. And secondly, we want to validate and compare our results. Because we want to be sure that whatever we implement in SpineOpt is also actually making sense. Yes, so let's look into the modeled system itself. For the scope, we had 24 hours of operation of a co-optimized power and gas system. We looked at 12 natural gas nodes and 24 electricity nodes. Both systems are schematically depicted to the right-hand side here. The details don't matter too much here, but what's important is that I have taken those pictures from Anna Schwele and their colleagues from their study on convexification approaches for line pack modeling. And this is also the test system that they described that they use, that we have used for our case study in SpineOpt. And luckily, these guys also published their input data online, which makes it for us really easy to really one-on-one compare our results. So thanks for that. And let's look at what the input data looked like. Well, for the gas side input, we knew already beforehand what the initial line pack of our gas pipelines, so the storage state at the beginning of the optimization looked like. We had some compression stations, and we knew the compression factors of those. We have some gas nodes present, and we know the minimum and maximum pressures and their time-dependent demands. And if we move to the right-hand side, we have the electricity system inputs. Here we have some transmission lines with predefined capacities, minimum and maximum voltage angles, and line susceptance. On top of that, we have some units. And if I look at the electricity system inputs, these units, I'm referring to the ones that are non-gas fired. So there's some other units in the system. For example, also the wind turbines, for which we have an availability factor. We know our fuel costs for those units. And to make the system, of course, a bit more realistic, we have an electricity demand as well. And in between those two systems, we have our gas-fired power plants, for which we know the capacity and the conversion factor from gas to electricity. And as we're all modeler, or let's say most of us are modelers, we know that no model is perfect. And every time we are making some assumptions. And in this case study, we have taken the following assumptions. We're assuming that on the gas side, that we are isothermal, that we have a constant compression factor of the compressor stations. And these compressor stations also, we are not taking into account the fuel that those compressor stations are consuming. And we're assuming that we can approximate the Weymouth equation, which describes the pressure-dependent steady-state gas flow. And this equation is non-convex and it's non-linear. So we're assuming that we can outer approximate this Weymouth equation around fixed pressure points. And on the right-hand side for the electricity system, we're taking the assumption that this is a lossless DC model. But this is, even though these are assumptions, but still we are including quite a bit of technical detail here. And that was also the challenge of this case study. So on the one hand, we have our generic SpineOpt building blocks, and at the same time, we have these specific commodity physics. And I think we managed quite nicely to represent both of these in SpineOpt. And for this, to illustrate this a little bit, I brought here the graph through from this case study. On the left-hand side here, we see the gas network. The symbols are a bit small, and there's some very small writing, but that's not important here. The important thing is that we see red, green, and blue. And red, you might have already recognized from previous presentations, are our units, which in this gas network present our gas producers. Then in green, we have our connections in the gas network. Those present the gas pipelines. And in blue, we have our nodes that in the gas network represent either the gas nodes or the storage capability of those pipelines. And what we see is that this flower graph view kind of agglomerates around the center. And in the center, we have the commodity, which is gas. And if we look now to the other side of the system, we see that the electricity network, even though it's a completely different physics, but again, we can find the same elements. So again, we have our units. And if we look at the electricity network, those are the ones that are to the right-hand side here. These ones are not connected to the gas network. These ones are non-gas fired units, so power plants. In green, we have the electricity lines, the connections, and in blue, we have our nodes that are here, electricity buses. And again, everything agglomerates around the commodity, electricity in this case. And to bring those two networks together, well, we have in the middle, obviously, our gas-fired power plants. So those are really the coupling entity in this example that are gas-fired and produce electricity. Perfect. So what was the outcome from this particular gas study? Well, I brought some small results, but more a conclusion. The conclusion of this case study is basically great. We can model this technical detail of SpineOpt. That should be the takeaway from this case study. And what we wanted to do is we wanted to co-optimize the operation of the power and gas dispatch, including DC power flow equations and pressure-driven gas transfer. Did we manage to do that? I believe so. If we look at the left-hand graphic from this the upper left graph, we have in blue the gas production and in red the gas consumption. And those are, let's say, timely shifted. They are not exactly the same over time. And this is also represented when we look at the right-hand side. What's illustrated here is just the line pack of the system, and we see that there's some charging and discharging processes happening, representing the line pack flexibility. And our second objective was to validate and to compare results. And I think that worked out pretty well as well. We took this study from Anna Schwele and her colleagues, compared the objective function and compared the line pack flexibility and saw that this was indeed reproducible. And here down there's two examples. On the one hand, in blue, the original line pack of pipeline I1, and in red, the replicated case study. And this was in very few words and slides our gas grid study. And with that, I'm gonna give the mic to the next speaker, which I think is Manuel on the stochastics.
Thank you, Maren. Thank you so much. Nice presentation. So yeah, the next case study is about stochastics. So we are trying this presentation to cover relatively wide spectrum of applications, so you can get an idea of what's possible with Spine Tools and SpineOpt. For the stochastic, we have an example here that it's not part of the official Spine case studies, but that something that we implemented specifically for this presentation. The idea here is to illustrate the concepts rather than to provide a very nice case study with a lot of data and nice results. So be aware that this is not going to be too awesome, but I think you will appreciate the concept that it's behind. So the thing is that SpineOpt is very particular in the sense that you can define multiple stochastic structures and assign these stochastic structures to different elements of your model. And that's often a requirement for multi-energy systems where some parts of your model are just deterministic, so you don't want any stochastics there, and some other parts are stochastic and you want the stochastic complexity only there, so your model doesn't grow larger than it has to. So we're going to try to use that. For this, we're going to take a simple two-stage stochastic problem, which I will describe next. So this is an exercise from a KTH course. So you will see that it's described sort of like for students. So there's a company that owns 4 hydropower plants and trades electricity on the market. The electricity prices are uncertain, but there are 4 scenarios that are equally probable. So 0.25 weight on each of them. And the company has an accurate forecast of the electricity price for the next 6 hours for each of these scenarios. And the interesting thing is that the companies offered a bilateral contract to sell a fixed amount of electricity during 4 of these 6 next hours, so hours 2 to 5. And the objective here is to maximize the income of electricity plus the value of stored water, so the value of the water that is left in all 4 reservoirs at the end of the 6 hours. And the two-stage thing comes from this 2 bullet points here. So in the first stage, the company needs to decide whether or not to accept the bilateral contract. So this is a deterministic decision that needs to be taken beforehand, and it needs to be the same for all the 4 scenarios. And in the second stage, the company can determine the actual operation of the power plants and the market trading that better suits each of the scenarios. So here's the input data we have. So it's pretty simple. The 4 power plants are in line, and we are ignoring delays in this case. So it's just like an electricity system of sorts where the water just reaches the next station instantly. But they are also located in line, as I was just saying. So it's pretty simple. And here you have our electricity prices in money per megawatt hour for the 4 scenarios and the next 6 hours, and also the value of the water in the future for the 4 scenarios. So this is a pretty simple system. We can see how this is implemented in a SpineOpt. So we begin by laying out our power stations. So we have 1 reservoir per station that releases water into a power plant, and then that power plant releases the same water onto the next reservoir, basically. And you have that times 4. At the bottom, there is a downstream node, which represents like the sea or whatever. That is not drawn in this picture, but you can imagine that the cell power plant is releasing water somewhere. And then all the power plants are connected to an electricity node. So this again is very similar to the hydro example. The electricity node is trading with a unit here. And you see that there are two links between the electricity node and the electricity trading, and this represents buying and selling. So for each of the two links, we have a different cost, which is negative in one case and positive in the other case. And the cost, of course, is the negative of the price. And then there's a unit connected to all four reservoirs that is used to compute the value of the future water. So this unit is allowed to function only at the very last time step. So we fix the flow of this unit for all the for the 5 first time steps, if you will, and we leave it free in the last time step. So the effect that this will have is that in the last time step, the unit will take all the water that is in the reservoir at that point, and it has assigned a cost. So when the water flows into this unit, it does it at a cost, and that cost is a negative cost, and it's a negative value of the future water. So this is kind of a clever way of modeling things in SpineOpt. Sometimes you need to come out with these interesting strategies of modeling. And then connected to the electricity node, you have the bilateral contract unit. It's basically buying this fixed amount of electricity on a specific period of time, so from hours 2 to 5, and that's also again controlled by fixing the no, actually this is sorry, I was mistaken. This is controlled by using a temporal block that is only assigned to this, only attached to this unit, and this temporal block goes from hours 2 to 5 only. So that's how we fix the flow to 0 in the first and 6th hours. And as we were seeing in the description of the case, the bilateral contract is a deterministic decision. So we define a stochastic structure that we call det for deterministic, and it has a single scenario that we call first state, and we associate that stochastic structure to this unit. And everything else is stochastic. Every other unit is connected to this fan stochastic structure that has the 4 scenarios in a fan. So they are basically equally probable. Well, that's defined by a parameter. But what we see here is that they are simultaneous, which means that they happen at the same time and there's no branching or converging. As a side note, branching and converging is allowed by SpineOpt. So you can basically build very complex stochastic structures where you have like basically it's a graph, a directed graph, where you define parent-children relationships to express how your stochasticity is actually happening. But this is not the case for this example. So we can solve this with SpineOpt, of course, and we can get trajectories. So this is why I was warning you that this is not very impressive, but we see. So what we see here is the reservoir level for 2 of the power plants over time, and also for the different scenarios. So you can see how the model is optimizing the different trajectories depending on the actual prices that are valid for each scenario. So we have increasing or decreasing trajectories. This is the reservoir level for the other 2 power stations. So we see stuff is happening here. But again, let me just show you how this looks in the Spine toolbox. So I have a project that I call Simple System. No, it's called Stochastic Hydro. Excuse me. Here I have something else in the workflow because I want to export the results from the database into a CSV file that I then pass to this tool. And this tool is, if I can show you, it's a Python tool that basically uses the matplotlib package to plot the results because I wanted some custom plotting. But the main thing I wanted to show you is in the input data store. I just wanted to show you how do we specify the stochastic parameters, and this is done by something that we call a map. So for example, let me find the electricity trading unit. So you see that for the electricity trading unit, we have the VOM cost parameter. By the way, if I hover a parameter name, I can see a brief explanation of what this is referring to. So it's the variable operating cost of a unit flow variable. So here I have the link from the node and to the node because I'm buying and selling. And here I have the value, which is a map. And if I open it, I can see that I have a mapping from scenario name to a time series. And then I can open the time series, and I finally see the price or the cost. In this case, it's a negative cost, so it's a price. So this is the one that I'm using to sell because I'm making money with this. So here I just have the data in the time series. And for different scenarios, I have, of course, a different time series. And the other important thing is that these labels here are named exactly as my scenarios, like this, send 1, 2, 3, 4. So only by doing that, SpineOpt will interpret this as a stochastic time series, and I will do the right thing to build an optimization problem that takes care of these stochastics as it should. So yeah, that's pretty much all I had to say about this. Maybe since we have some time, I can briefly show you. So this is the results database. We have what I was showing you in the slide. For different stochastic scenario, I have different reservoir levels. So this is what we call node state, is a reservoir level. And here I can see the trajectories. And I can also see that at the very last time step, I don't have any water left because the future value unit has taken everything. One can plot right here like this. So if you want a quick plot, you can have it. Well, okay. But then if you need something like more specific, you can, of course, use something else like I'm doing. Here are different runs, as I was saying before. Unfortunately, what I'm doing here is just running the same system over and over for some reason. So I don't see any difference in the result. But of course, if between runs I change my input data, I will, of course, see the differences in the results as well. And this is why this is interesting, because I can quickly compare different runs. Maybe we can show you an example later. And this is the exporter, since I have a few minutes. The exporter basically sniffs the output database and just outputs data from that database into tables. And I can specify like a mapping here where I can select where do I want to put each database element in the table. So Basically, I enter a number, which is the column, and I can pivot stuff if I want. I didn't prepare anything for this, so I don't want to mess too much with it. But the point is that you can define a mapping from the database into tables. So it's better for you, like, to do some post-processing, perhaps. So that's basically it. I think I can go back to the presentation now to go into the last case study. If somebody can share the slides for me. So I'm a Linux user, so I cannot use all the functionalities from Teams, but I wanted to say that Spine Toolbox is fully multi-platform, or at least it tries to be fully multi-platform. So you can use it basically from Windows, Linux, and Mac, regardless. So this is our last case study presentation. It's about investments on the power grid. This has more interesting results. This is one of the what we call C case studies, which were performed later in the project and are intended to kind of push Spine capabilities to the state of the art. That's at least our ambition. And we want to do here, what we want to do here is to build a long-term power grid investment model of the Nordic system, or of part of the Nordic system, if I can be honest. And we want to capture operational detail to the largest extent possible, while still being able to solve this in reasonable time. That's basically our setup. I'm trying to present here the tension that exists between extending the time horizon for investment models and handling multiple scenarios, while at the same time trying to capture the operational detail at a high resolution. That typically leads to tractability issues or performance issues, if you want. And what we will do in practice is we will take data from the N490 model of the Nordic synchronous power grid system that we have developed at KTH for a number of years. So it's basically a spatial disaggregation technique that we are using to kind of compute parameter values for generators and for lines, increasing the granularity, if you want. So we have a high granularity, high granularity. No, well, increasing the resolution, maybe. So we have data in a high spatial resolution, no, low spatial resolution, we want to make it higher, so more detail. And it includes Norway, Sweden, Denmark, and Finland. And it's basically DC power flow data, and it includes the grid. And we want to use these two features here of Spine to improve computing time. So we have this parallel scenario execution in Spine Toolbox that we can use. So multiple scenarios are running parallel. And we also have implemented this vendor's decomposition approach in a SpineOpt. So we can decompose the investments and operations problem. And as if you're familiar with this, I'm not very much. But if you're familiar with this, you should know that this is like an iterative process where you add cats to a master problem based on the marginal value of some constraints in the sub-problems. And it increases efficiency. So our approach is the following. First, we will run SpineOpt with the data, the Nordic data. And we will compute line flows. So no investments here, just operation. And we get results for the power that is flowing over the lines. And then we have a value for the capacity of each line from the same Nordic data. So we will compare the flows that we obtain from SpineOpt with the capacities, and we will determine a measure of how congested the line is. That's our approach. And then we go to the third step, where we basically rank these lines per congestion index, and we select the most congested ones as investment candidates. And then we run SpineOpt a second time, and now we include the investment variables to compute basically the final investment decision. So which of these candidate lines are invested in the end. So you see that SpineOpt is used twice. Thanks to its flexibility, SpineOpt can run an operation problem only, but it can also run an operation plus investments problem if you set up the data correctly, basically. And we have this nice workflow that does what I just described. This block here on the left is basically where we import the Nordic data that we have in an Excel file. It comes in an Excel file. And we use an importer to bring it into a Spine database. It's pretty simple. And we also load some template data that we have for SpineOpt that basically simplifies the task of building a SpineOpt database. Then the second block runs SpineOpt, operations only, and writes result in this output data store. Then we have a block here where we do the candidate line selection thing. We export the line flows into a table to feed that to a Python script that uses pandas package to do some data frame computation and sorting the lines basically by congestion index, sorry. And then we select some of them and we import them back into a Spine database here, that the candidate lines database. It has only the candidate lines. And then we have a third block, which is basically a second import operation where we bring a lot of data into our Spine database that now has operation plus investments data. So we have the original data from the N490 model, plus the candidate lines we have computed, plus some wind scenarios that we want to use for this investments model. So we have 3 scenarios of wind, and we basically have some tools and importers here to bring that wind scenario data as time series into the Spine database. And then the last thing is just to run SpineOpt on this database that has been set up to make SpineOpt compute investments decisions. And that's it, and we write results. So that's our workflow. And now results. So here we have a very big graph view diagram that basically shows the Nordic 490 data when it's just imported into a Spine database, so we can have this visualization tool. And again, we need to pay attention just to colors here. So we have in red generating units. So we see that they are mostly concentrated in the top part of this diagram. And then we have in green, we have a lot of connections, of course, and then in blue, we have the nodes. These are not the actual geographical locations. This is just kind of something that optimizes the placement of the vertices, so you can see as clear as possible. And then this is what happens when we select candidate lines. So these are in yellow here. You can see these are the 100 most congested lines as we computed using our technique I just explained. You should know that these candidates are selected as existing lines. So we only have candidates where we also have an existing line. Because of the way we compute the candidates by comparing flows to capacity. So we are considering changing the technique so we can select candidates from any 2 pair of nodes, basically. But this is what we have so far. So it's basically like an investment on capacity, I should say. So these are the candidate lines. And finally, these are the lines that are selected by the second SpineOpt run. So it's only 14 lines that are invested in at the end. And it's really reasonable to me, this result. So the system, the SpineOpt is basically trying to reinforce this lower part of the system that is not very well connected to everything else, and it has not much generation. So these results make sense that way. And a side result is that it's very affordable, in my opinion. It only requires 2 vendors iterations to convert for some reason, which seems like very little. So maybe there's something to look after there. And in total, it's 6 hours of wall time. So I ran this, and at the same time, I was just using my computer, and it was only a little bit slower. So I think this is I was really happy with this, because it means that you can experiment a lot with this and change data and run again and see what happens. So in conclusion, I can say that Spine Toolbox and SpineOpt can be used effectively for this kind of modeling. The vendors decomposition and the parallel scenario execution help in getting results in affordable time. I have some ideas for future work here that I maybe was mentioning during the presentation. So maybe have a better methodology to select the candidate lines, use representative periods, because we have tools for that, and SpineOpt can also handle that in a very graceful manner. So maybe we can try that. We want to model hydro generators more accurately, because now they are just like conventional generators that just dispatch, so no reservoir, nothing like that. Maybe this is a little bit crazy, but maybe we can combine this model with the hydropower model we have. We have an hydropower, I didn't say this, but we have an hydropower model of the Nordic system as well. So maybe we can link these two together. And then we aren't using the investment cost or the lifetime, and that's also allowed by SpineOpt. So, and it would be very straightforward to do. So maybe we can try to do that in the future. So that's it. I will give the floor back to Juha for this last slide.
All right, thank you very much, Manuel. I found it very interesting, but I'm biased. So here is a slide where you can see a little bit of our contacts, and also you can even press the links yourselves to get to the pages where we have our stuff. And then, of course, if you're interested in some form of collaboration in future, please take contact. We will have good time for Q&A. We had some questions, and I think we have quite a few of them already answered in the chat, but I really encourage you, if you have any more things to ask, there's only good questions. We want to learn from you what was interesting, and also what might not have been clear, and so forth. There's a question that will we collect the Q&A? Yes. We have it. We will keep the chat so we can have the questions also afterwards. And of course, those that we are able to answer here in the webinar, they will be available. And if we can't answer everything, we can also get back to you, or even use our repositories as a way to improve documentation and so forth. There's at least one question that's that could be maybe a little bit expanded. Leonardo asked there that when he has input data that is not saved per time step, but there is a certain amount of energy being consumed, but at the same time the output should be based on a fixed time step, and he's asking whether this could be somehow managed in SpineOpt. And if you didn't quite understand the question, then please ask Leonardo for a bit of a clarification. Is that Manuel? Would you want to have some more clarification on that one, or?
Yeah, of course.
So
But I didn't understand the question fully.
Yeah, I'm just allowing Leonardo to speak up. So.
Okay, can you hear me?
Yes.
Yes, no, in reality, you already answered to me, because I have a. That's right. How Juha has understood. It's a sort of a counter where you after 300 kilowatt hours are used. I have a time step and the use of 300 kilowatt hours. So in the reality, I can transform this quite easily, as I asked upper, in a variable time step, because this is what I have. The comment that was not a question. There was the comment. Someone asked why this kind of. I just wanted to explain why this kind of not fixed time step. It's because I have this kind of data, but it's equivalent absolutely to a variable time step. So as far as I understand from your answers, it is possible to manage variable time steps. So and then have an output as a fixed time step. So it's clear for me, at least.
Perfect. Yeah. It's possible. You can have a
Yeah.
fixed time step or a variable, and it's whatever you need, basically.
Yes, because for example, in the Arena Flex tool, as far as I have tried to use it, as far as I have used it, the time step is fixed, and so for this kind of problems, is not possible to use it.
Yeah. That's right. The next version of Arena Flex tool will have a variable time step, but let's see when that.
Okay. The next, there will be a next.
Please try SpineOpt now.
Yeah. Yes. But this is interesting. So this is okay. A kind of news. Okay. You are preparing a second an Arena 2.0. So
yeah, actually 3.0. Yeah.
3.
Okay.
Yeah. Okay. Thank you, Juha.
Let's get back to the SpineOpt. So there was also a question from Kenneth, who unfortunately had to leave already, but he was asking about that extension of the gas model, and then he continued with a question about the multimodal capabilities of SpineOpt. So maybe Maren or Manuel, you want to kind of expand a little bit how that multimodal thing works.
Maren?
Good question. So, I mean, I'm not exactly sure what exactly we were referring to when we talked about multimodal, because actually when you're talking about the spine family, there's two multi-models. On the one hand, you can have multiple models in your spine toolbox workflow. So you can, as Manuel was showing with this little hammer, you can have different tools that are interacting through spine toolbox. So that's the one side. And then we have in our SpineOpt database. So that's where we saw, these wonderful graphs of flowers, how I called them. There it's actually possible to have more than just one model. But those are then SpineOpt models. So if you were to include a non-linear gas flow, you would have to include this. If you were to go for the SpineOpt path to this, you would need to include this into SpineOpt. And yeah, to come back to that question, that would mean in practice, you would need to add these non-linear, non-convex equations, which sounds straightforward. But as I mentioned in the chat, SpineOpt is formulated as a mixed integer linear problem. And to be frank, I have not tried to enter non-linear equations in SpineOpt. I doubt it would work out of the box. So I do think we would need to do some adaptations for sure. I hope that was sufficient.
All right, thank you. We could have more questions either in the chat, or then you can just raise your hand if you have something you want to ask. Otherwise, we will need to stop early. So it seems we are not getting more questions unless someone is typing right now, but I think it's then time to conclude the webinar. Big thanks to the presenters. You did a great job. And thanks for the audience for being here and listening to our stuff. Thanks. Bye-bye.
Bye, everybody.
Thank you. Bye-bye.
Thank you.